think about this for a second. From like ancient markings on bones tracking the moon to these super high-tech laser systems detecting gravitational waves. We humans, we've always had this fundamental need to measure things, to
Yeah.
know exactly how much, how far, how long. It's just core to how we make sense of everything.
It really is. And what's amazing is how this basic drive led to, well, these incredibly complex but often invisible systems we have today. It's not just about getting a number, is it? It's about creating a shared language,
Yeah.
you know, a way to talk about reality accurately.
And that's exactly what we're diving into today. We had a listener ask about the real foundations of measurement, the basic units, length, mass, time, and how we actually measure them. So we've gathered some great material covering everything from the SI system to things like vernier calipers, screw gauges, even the simple pendulum.
Right. And our mission here is to sort of unpack the essential ideas. We want to give you that aha moment about why units are the way they are and how these tools actually work without, getting totally bogged down in technical details.
Exactly. We want to get the why behind the what.
Precisely. Understanding the principles.
Okay, so let's kick things off with something that seems maybe obvious, but it's totally fundamental. Why do we even need units?
Well, at its most basic level, measurement is just comparison, isn't it? You can't just say something is long. You need a reference. And that agreed upon reference, that standard amount of something, well, that's what we call a unit.
Right. So if I say I have 10 meters of cloth, that 10 only means something because we all agree on what a meter is. It tells you the cloth is, well, 10 times that standard length.
Exactly.
Or like 5 kilograms of sugar. The mass is 5 times the standard kilogram. Without that shared understanding, it's just vague.
Spot on. But it's not enough just to have a standard. A good unit needs to meet certain criteria. It needs to be a convenient size, for one. Imagine measuring a book in kilometers, right?
Yeah, it wouldn't work well.
And it needs a really clear, unambiguous definition. Everyone, everywhere, has to know exactly what it means. Then, crucially, it must be reproducible. We have to be able to make that standard reliably. And maybe the most important thing for science across borders, it has to be invariant. Its value can't change depending on where you are or when you measure it. That stability is key.
That makes total sense. Now, our sources talk about fundamental versus derived units. What's the main difference there?
Okay, think of fundamental units as the absolute basics, the building blocks. They represent quantities that are independent. You can't get them by combining other units. In the SI system, which is the standard now, there are 7 of these. Length, the meter; mass, the kilogram; time, the second; temperature, the Kelvin; luminous intensity, the candela; electric current, the ampere; and amount of substance, the mole. Plus 2 supplementary ones for angles, the radian and steradian.
So these 7 are like the elements of measurement in SI. Everything else is made from them.
Pretty much, yeah. Derived units are exactly that. They're derived from or depend on the fundamental units, usually through multiplying or dividing. Take area. That's length times breadth, right? Both length units. So the derived unit is square meters, $2 too.
Okay.
Volume is length times breadth times height, cubic meters, 23 in hours,
Yeah.
speed. That's distance, which is length, divided by time. So meters per second, a lentisol.
Ah, I see. So you combine the fundamental ones to describe more complex things.
Exactly. Like pressure, for instance. That's force over area. Its SI unit, the Pascal, is actually a combination of kilograms, meters, and seconds.
Yeah.
Energy M1, S2. It all connects back. It's quite elegant, really.
The sources also mention some older systems, CGS, FPS, MKS. Where did they fit in?
Yeah, those are mostly historical now, though you might still bump into them sometimes. CGS was centimeter, gram, second. FPS, foot, pound, second, common in some places historically. MKS used the meter, kilogram, second. That one was really the direct forerunner to SI.
So SI basically won out.
Yes, largely because it's so coherent. All the derived units link directly to the base units without weird conversion factors. Plus, it's just easier to use and internationally accepted.
Okay, SI is king. Let's look closer at it. We've got the 7 fundamental units. But how do we handle really, really big or incredibly tiny measurements?
That's where SI prefixes are brilliant. The system uses a standard set of prefixes. They basically act as multipliers, powers of 10 for the base units. For big stuff, you have deca, kilo 1/3, mega 162, and giga 109, and all the way up to yada. And for tiny things, deci $10, centi 10.21, micro 10.3, right down to yocto 1024 tac.
Gotcha. So when my Wi-Fi says 2.5 gigahertz, that's just 2.5 times 10 to the 9 hertz.
Exact.
Or a tiny capacitor rated at 5.0 PF is 5-point nerd times 10 to the minus 12 farads. It's like a universal shorthand, avoids all those zeros.
Precisely. It's super convenient and unambiguous across just a massive range of scales.
Okay, great. So with that sailing in mind, let's dig into the fundamental units themselves, starting with length.
All right, length. The SI unit is the meter, symbol M.
And its definition has changed quite a bit over time, hasn't it? That's fascinating.
It really shows our constant quest for more accuracy, more universality. Originally, back in 1889, it was literally the distance between two scratches on a platinum iridium bar kept in Paris.
A physical object.
Yeah, but physical things can change, even slightly. So in 1960, they moved to defining it based on the wavelength of light from Krypton 86, much more reproducible.
Better, but still based on a specific element.
Right. But the current definition from 1983 is maybe the most fundamental. 1 meter is defined as the distance light travels in a vacuum in 1 divided by 299,792,458 of a second.
Wow, so it's tied to the speed of light.
Exactly. It anchors our unit of length to a universal constant. You can't get much more stable than that.
That's actually mind-blowing. Okay, but for everyday stuff, we use smaller bits of a meter.
Oh, absolutely. The centimeter, 1002 meters, the millimeter, 1003 meters. Then you get smaller. The micrometer, often called a micron, 10 is the years, and the nanometer. These are used all the time in engineering, science, even tailoring. Nanotechnology relies heavily on nanometers.
And for really big distances.
Well, on Earth, the kilometer 133 meters is standard. But out in space, we need bigger yardsticks. There's the astronomical unit, or AU, that's the average Earth-Sun distance, about $1.05 times 10 meters.
Huge.
Then the light year, the distance light travels in a year, that's massive, about $9.01 times 1015 meters. And astronomers also use the parsec, which is about 3.26 light years, or $3.01 times 106 meters.
Hard to even imagine those scales.
We even use light minutes and light seconds for distances within the solar system sometimes.
The sources also mention angstroms and firmus, smaller units.
Yeah, the angstrom is 10 meters. It was used a lot for atomic sizes and light wavelengths, but nowadays the nanometer is often preferred. The Fermi F, which is 1015 meters, is tiny. It's used mainly in nuclear physics for things inside the atom's nucleus.
Okay, let's switch gears to mass. SI unit, the kilogram. Kilo. Similar story with this definition, right? Tied to a physical thing.
Yes, for a very long time, over a century, the kilogram was the mass of a specific platinum iridium cylinder. The International Prototype Kilogram, also kept near Paris. Fun fact, the mass of a liter of water at 4 degrees C is very close to a kilogram, historically.
But that changed recently.
It did. A huge change in 2019. Now, the kilogram is defined based on Planck's constant, a fundamental constant from quantum mechanics. So like the meter, it's now tied to an unchanging law of nature, not a physical object that could theoretically change mass.
More stable, more universal. Makes sense. And we use prefixes for mass, too.
Yep, same idea. Common small units are the gram 10 3 kilograms and the milligram 10 psych are used everywhere, from cooking to medicine. For larger amounts, you hear about the quintal 100 kilograms and the metric ton 1,000 kilograms, especially in industry or agriculture.
What about this atomic mass unit mentioned?
The AMU, or sometimes just U. It's not an SI unit, but it's vital for chemistry and physics. It's defined as exactly 1/12 the mass of a carbon-12 atom. It's tiny, about $1.66 times 1027 kilograms. Perfect for talking about the mass of single atoms or molecules.
And for really huge masses, like stars.
Right. Astronomers often use the solar mass, the mass of our sun, which is roughly $2 times 10 kilograms. It gives a relatable scale for galaxies and other stars.
Okay, mass covered. Let's move to time. The SI unit is the second S. Its definition also evolved quite a bit.
Oh, definitely. It started out based on astronomy specifically, 186,400th of the average solar day. The average time it takes Earth to rotate once.
Seems reasonable.
But the Earth's rotation isn't perfectly constant. So for more precision, it was redefined based on the length of the year 1900. But the current definition, since 1967, is atomic. It's based on the vibrations, or rather the radiation frequency, of a cesium-133 atom. 1 second is defined as the time for exactly 9,192,631,770 cycles of that specific cesium radiation.
Wow, that sounds incredibly precise.
It is. Atomic clocks based on this are astonishingly accurate. The precision is absolutely essential for things like GPS navigation, communication networks, lots of modern tech.
Amazing. And what about the everyday units of time, smaller and larger than a second?
Sure. Smaller ones include the millisecond, 10 to 3 hours, microsecond, 10 nanosecond, vital in electronics and computing. There's even an informal unit, the shake, sometimes used in nuclear physics.
The shake. Never heard that one.
Yeah. And going bigger, we have the familiar minute, 60s, hour, 3600s, day, 86,400s. Then things get a bit more complex.
Yeah.
The month, variable length. The lunar month, about 29.5 days. The year, about 365.24 days.
Which leads to leap years.
Exactly. We add a day nearly every 4 years, February 29th, to keep the calendar aligned with the Earth's orbit. The rule is usually, if the year is divisible by 4, it's a leap year. Unless it's a century year, like 1900, 2100, then it also has to be divisible by 400 to be a leap year. So 2000 was a leap year, but 1900 wasn't.
Right. Got it.
Then we have the decade, 10 years, the century, 100 years. Interesting point on centuries. The first century AD was years 1 to 100. So the 20th was 1901, 2000, and we're in the 21st, 2001, 2100.
Oh, that catches people out.
And finally, the millennium,
Yeah.
1,000 years, all ultimately traceable back to that cesium atom stick.
Incredible. Okay, we touched on derived units earlier. The sources list quite a few. Maybe walk through a couple more.
Sure. We did area, volume, barrage speed. Density is mass per volume, so its unit is kilograms per cubic meter. Kilos is in pretty plas. Acceleration, how quickly velocity changes, is meters per second squared. Then there's force, the push or pull. The SI unit is the Newton, named after Isaac Newton, of course. Fundamentally, a Newton is kilousm SD.
And yeah, it's cool how many are named after scientists, like a built-in history lesson.
There really is a great tribute. Work or energy is measured in joules, Che, after James Prescott Joule. A joule is kilo-TS2. Power, the rate of energy transfer, is in watts, W, after James Watt. That's kilo-TeV3 Dal. Pressure, force per area, is in pascals, after Blaise Pascal, kilo-TM1S2. Frequency, cycles per second, is in hertz, after Heinrich Hertz.
Okay, and electrical units too.
Yep. Electric charge is in coulombs, C, after Charles Augustin de Coulomb. That's ampere seconds, AS. Electric potential or voltage is in volts, V, after Alessandro Volta, kilo-GM1S3. And electrical resistance is in ohms, after Georg Ohm, TIS3. You see how they all build up from those 7 fundamental units plus the ampere for electrical ones?
Definitely. Now, the sources also give some really important rules for how to write these units and symbols correctly. Seems minor, but crucial for clarity.
Absolutely vital. These conventions stop confusion, basically. Symbols for units not named after people are lowercase.
Yeah.
MS, KG. But if the unit is named after someone, the symbol starts with a capital letter. N for Newton, J for joule, V for volt.
Okay, symbols capitalized if named after a person.
But, and this is important, when you write out the full name of the unit, it's always lowercase.
Yeah.
Even if named after someone. So Newton, joule, volt, meter, kilogram.
Got it. Lowercase for full names, always.
Right. When you multiply units, use a dot, a cross, or just a space between symbols, like N more and NM for Newton meter. For division, use negative exponents. So meters per second is -1 N, much cleaner than M sometimes.
Okay.
And a big one. Unit symbols are never plural. It's 10 meters, not 10 meters, because means milliseconds.
Ah, yeah, that could cause problems.
Definitely. Also, use only one prefix at a time. Gigawatt, GW, it's fine, but don't write kilomegawatt, KW. Just use the single correct prefix.
Makes it.
And finally, remember that a prefix and symbol together make a new unit symbol. If you cube it, you cube the whole thing. So kilomem threes isn't 103 millimeter threes, it's 103 millimeter threes, which is 109 millimeter threes.
Good rules to remember. Okay, let's shift to the practical side. Measuring length with more precision than a ruler. Vernier calipers and screw gauges. What's the basic idea behind them?
Both are clever ways to measure much smaller fractions of a millimeter than you can see on a standard ruler.
Yeah.
They work by letting you read between the main markings. The key concept is called the least count.
Least count.
Yeah, it's the smallest measurement the instrument can accurately make. Think of it as the instrument's resolution. Smaller least count means higher precision.
Okay, let's start with vernier calipers. How does it work?
A vernier uses 2 scales side by side. There's a fixed main scale, usually in millimeters, and a sliding vernier scale. The trick is that the divisions on the vernier scale are slightly smaller than the main scale divisions. Typically, new divisions on the vernier scale match the length of N1 divisions on the main scale.
That small difference is the key.
That's the magic, yeah. It allows you to measure fractions of a main scale division.
So how do you actually read it?
It's a 2-step process. First, you look where the 0 mark on the sliding vernier scale lands on the main scale. Read the main scale value just before the vernier 0. That's the main part of your reading.
Okay.
Then you look along the vernier scale until you find the one vernier division line that lines up perfectly with any line on the main scale. You note which vernier division number that is. Multiply that number by the instrument's least count. That gives you the fractional part.
And the total reading is just adding those 2 parts.
Exactly. Main scale reading plus coinciding vernier division times least count.
How do you find the least count itself?
The least count is the value of one main scale division divided by the total number of divisions on the vernier scale. So if the main scale is in millimeters, 1 millimeter divisions, and the vernier has 10 divisions, the least count is 1 millimeters, 10 is 0.1 millimeters, or 0.01 centimeters. Pretty neat.
Yeah. The source also shows the different parts, outside jaws, inside jaws.
Right. The big outside jaws measure external things, diameter of a rod, length of a block. The smaller inside jaws at the top are for internal measurements like the inside diameter of a tube. And there's usually a thin depth bar or strip that slides out the end. That's for measuring depths of holes. Plus a little screw to lock the sliding jaw, which helps when you're trying to read it carefully.
And these can have errors, right? Zero error.
Yes, like any precise tool. Zero error happens if, when the jaws are fully closed, the zero on the vernier scale doesn't line up perfectly with the zero on the main scale. If the vernier zero is to the right of the main scale zero, it's a positive zero error. If it's to the left, it's a negative zero error.
How do you figure out the value?
When the jaws are closed, you see which vernier division does line up with the main scale line. For positive error, multiply that division number by the least count. For negative error, it's a bit trickier. You find the coinciding division, then the error is negative, and its value is total vernier divisions coinciding division number times the least count.
Okay. And then you have to correct your actual measurement.
Exactly. The corrected reading is always observe reading zero error. Remembering the sign of the error. You have to subtract the error to get the true value.
Makes sense. Now, the screw gauge sounds even more precise.
Generally, yes. It works on a different idea. The principle of a screw. Turning the screw a precise amount makes it move forward or backward a precise linear distance. It has a U-shaped frame, a fixed anvil or stud, and the screw moves in a nut. You turn a thimble, which has a circular scale on it, usually 50 or 100 divisions. The screw's body, the sleeve, has a linear main scale, often marked in millimeters or half millimeters.
So the rotation translates into linear movement. How does that give precision?
The key is the pitch of the screw. That's how far the screw moves linearly for one full 360-degree turn of the thimble, maybe 1 millimeter, 0.5 millimeter. The least count is then the pitch divided by the number of divisions on the circular scale. So if the pitch is 0.5 millimeters and there are 100 divisions on the circular scale, the least count is 0.5 millimeter. 100 equals 0.005 millimeters.
Wow, that is tiny, much smaller than the vernier.
Yep. So higher potential precision for measuring very small things, like the diameter of a thin wire.
And reading it. Similar idea with two scales.
Kind of. First, read the main scale on the sleeve. Note the last full division visible before the edge of the thimble. That's the main scale reading. Then look at the circular scale. See which division line on the thimble lines up exactly with the main horizontal baseline on the sleeve. Multiply that circular scale division number by the least count. Your final measurement is the main scale reading plus that circular scale reading x least count value.
And I bet these have zero errors, too.
They do. Same idea as a vernier. Close the screw fully onto the stud. If the zero mark on the circular scale doesn't align with the baseline on the sleeve, there's a zero error. If the circular scale zero is below the baseline, it's positive error. If it's above the baseline, it's negative. You figure out which circular division does align, calculate the error using the least count, and again, the corrected reading is observed reading zero error with its sign.
Okay. The source also mentions backlash error for screw gauges. What's that about?
Backlash. That comes from tiny gaps or looseness in the screw threads. If you turn the thimble one way, then suddenly reverse direction, the screw might not move immediately because of that play.
Yeah.
To avoid errors from this, it's best practice to always make your final adjustment by turning the thimble in the same direction. If you overshoot, don't just back up a tiny bit, back off quite a way, then approach the measurement again, turning consistently in one direction.
Good tip. It's really cool seeing how we get progressively finer measurements, ruler, vernier, screw gauge. Each builds on the last. Okay, final topic. Measuring time with a simple pendulum. This feels quite different.
It is a different approach, yeah. Using periodic motion. An ideal simple pendulum is basically a heavy point mass, the bob, hanging from a massless, unstretchable string fixed at the top. Pull it aside slightly and let go. It swings back and forth due to gravity. That's the basic setup.
And there are specific terms used to describe its motion.
Right. An oscillation is one complete swing back and forth, returning to the start point and moving the same way. The period t is the time it takes for one full oscillation, measured in seconds. Frequency, F or N, is how many oscillations happen per second, measured in hertz. It's just the inverse of the period.
Quite
Time amplitude is the maximum distance the bob swings away from its center resting point. and the effective length is crucial. It's the distance from the suspension point right down to the center of gravity of the bob.
So if you wanted to measure the period, how would you do it accurately? Just time one swing.
You could, but it wouldn't be very accurate because of your reaction times starting and stopping the stopwatch. A much better way is to time, say, 20 or 30 complete oscillations. Let it swing. Start the watch as it passes the center, count the swings, stop the watch after 20 or 30 swings as it passes the center again. Then you divide the total time, measured by the number of oscillations you counted. That gives you a much more precise average time for one oscillation of the period.
Averaging reduces the error. Smart. Now, the source says there's a key link between the pendulum's length and its period.
Yes, this is a fundamental result. For small swings, the square of the time period, T202, is directly proportional to the effective length, L. So T2 procto L2. If you plot T22 versus L on a graph, you get a straight line going through the origin.
And that tells you something important.
It does. The slope of that line turns out to be equal to 4 televs/$1, where g is the acceleration due to gravity. So just by measuring the period of a pendulum with a known length, you can actually calculate the value of g in that location. It's a classic physics experiment.
Amazing that a simple swing tells you about gravity. What else affects the period?
Well, length is key. Longer pendulum means longer period. Brawler is proportional to squirrel dealer. That's why grandfather clocks have long pendulums. And temperature can affect length. Metal rods expand when hot, making the pendulum longer and the clock runs slow. If you stand up on a swing, you raise the center of gravity, shorten L, and swing faster. Gravity G is also key. Period is inversely proportional to the square root of G, propto 1 squared G Pte. So if you take a pendulum clock up a mountain where G is slightly weaker, it will run a bit slower.
Interesting. What about the weight of the bob?
Surprisingly, for small angles, the mass of the bob and what it's made of don't affect the period. And also for small swings, the amplitude, how far you pull it back initially, doesn't affect the period either. That's characteristic of simple harmonic motion.
So length and gravity are the main players. Is there a formula for the period?
Yes, the classic formula for a simple pendulum's period for small angles is TT equals 2 foursquared, or squaring both sides gives 222 equals 4 pi 2, LG, which shows that T2 versus L relationship clearly.
And finally, what's a seconds pendulum?
That's just a special name for a pendulum whose period is exactly 2 seconds. It takes 1 second to swing from one side to the other. Very convenient for timekeeping. Where gravity is about $9.08, like here on Earth's surface, the length needed for a seconds pendulum is very close to 1 meter, about 0.994 meters, actually.
Well, this has been a fantastic deep dive into the science of measurement. We've gone from why we need units at all, through fundamental versus derived, the history, how we measure length precisely with verniers and screw gauges, and the physics of the simple pendulum for time.
And it really highlights how crucial accurate measurement is, doesn't it? It's not just academic. It truly underpins, well, pretty much all of science and technology.
Right.
Everything from medicine to engineering to communications relies on it.
Absolutely. So maybe as you go about your day, you can notice the hidden world of measurement all around you. The timing in your phone, the weight of groceries, the dimensions in buildings. And here's something to think about. How did different cultures tackle measurement before global standards? What ingenious systems did they devise? Or think about the limits. How precisely can we measure things? What does the quest for ultimate precision mean for cutting-edge science like quantum computing or cosmology? It's a never-ending story, really.